Inside the interval of convergence, a power series can be thought of as a function. And since they can be thought of as functions, well, we can do calculus on functions. We can find derivatives and find integrals. It turns out this theorem, which we're not going to prove, but is true, is that for any power series, the series is both differentiable and integrable, meaning we can find both derivatives and integrals for all x's inside the interval of convergence. Moreover, derivatives and integrals are computed term by term. Meaning we'll write out the sum as each of the terms, and then to find the derivative of that power series, we're going to find the derivative of each individual term along the way, and then we can write that new sum as using sigma notation if necessary, or it'll just represent what the derivative. Same thing with the integrals. If you want to find the integral of a power series, as long as the x's you're looking at are inside of the integral of convergence, then we'll just write out each term of this power series and we'll find the integrals individually. I have two examples of this. The first is using the power series from the previous example in the previous video. And what we're going to find an expression for what the integral of this power series is from 0 to 0.1. Note that this series converges on the following interval from -1/3 to x to including +1/3. This again we showed in the previous example. And further, that the x's we're considering are from 0 to 0.1, and that 0 to 0.1 are inside of this interval. That they're a member of the interval convergence, meaning that it makes sense to find the integral of this power series because we're choosing x's that are in the interval convergence. We said to find the integral, we're going to find the integral of these terms term by term, and then we'll sum together at the end. When I look at this integral from 0 to 0.1, when I look at this from n equals 0 to 0.1, to infinity, of -3 to the n x to the n over square root of n plus 1. That in this sum, in this integral, is dx, and this is important. That this is an integral with respect to x. So all the unknowns that are not x's, in particular this -3 to the n and the square root of n plus 1, these do not involve the term x. So in the eyes of this integral, that these terms are constant terms. The only thing that's a variable that we're going to be integrating that's going to change is this thing that's got an x in it. So term by term, what this tells me is that this integral is really the same as, well, I'm going to add together a bunch of terms that have the form -3 to the n over root n plus 1. Then I need to find, and then this is, each of these terms are going to get multiplied by the integral from 0 to 0.1 of x to the n dx. And each term is going to have something of this form, and then I'm going to sum them all together for increasing values of n. We know how to find this type of integral. This is the most basic sort of integral we find. So this is the power rule. So for each term of this form, this will just be, I'm just copying down the stuff that doesn't change. And then this integral is just x to the increase the exponent by 1 and divide by the new exponent. And I'm going to evaluate this for x's between 0 and 0.1. This is pretty easy to evaluate because 0, when I plug in 0 for x, this is 0 to increasing powers, which is 0. 0 time divided by anything is 0. 0 times anything is 0. When I substitute in 0, this entire expression is just sums a bunch of zeros, which is, well, 0. When I plug in 0.1, I get something a little more interesting, and that's just replacing x with 0.1. So I think an expression that would tell us how to calculate the value of this integral is sum from 0 to infinity of -3 to the n times 0.1 to the n plus 1 over n plus 1 times the square root of n plus 1. This is a convergent series. It converges some value. I don't really know what. Your calculator could approximate it if you plugged in ever-increasing values of n and type the sum into your calculator and hit enter. It or a computer can approximate what this sum is. It's not important to this problem exactly what the sum is, just that this is the expression you would get. But if you'd like to get an approximate value, again, you could use your summation on your calculator and just, instead of infinity, choose something in numbers that are increasingly large until the value starts stabilizing. Another example is this one. We have a function that's represented by a power series. We're going to ask to do some calculus on this, and specifically we're going to find the derivative of this function, and then moreover we're going to determine a common name we give this power series. So it turns out that this power series is actually a representation of a function we actually are very familiar with. We may not know it at the outset, but we'll look at some properties of this function and match this up with a function with the same properties. You have the same properties, you're going to be the same function. If we're going to find the derivative of this function, we need to make sure we know when this derivative makes sense. So before you can actually calculate this derivative, we need to know when this derivative makes sense. We need to know the interval of convergence. So we got to find the interval of convergence first. IOC interval of convergence first. So the ratio test tells us how to do that. It's the limit as n approaches infinity of the n plus first term over the nth term. Which is this limit as n approaches infinity of x to the n plus 1 over x to the n times n factorial over n plus 1 factorial. This ratio we've seen plenty of times. That's the absolute value of x. N factorial divided by n plus 1 factorial is 1 over n plus 1. And the limit of 1 over n plus 1 as n tends to infinity is 1 over infinity, which is 0. Absolute value of x times 0 less than 1. This is true for all real numbers, meaning the interval convergence. So the interval of convergence is the entire real line, or any real number. This is really good because this means that this function is defined, or this function and therefore its derivative are defined for every possible x. So we want to find what this derivative is. We're going to do derivatives term by term. I'm going to write out a bunch of the terms here so we get a feel for what this is. The sum is, or the rule is x to the n over n factorial. So the first is x to the 0 over 0 factorial. X to the 0 is 1, 0 factorial is 1. X to the 1 over 1 factorial is x. X to the 2 over 2 factorial. X to the 3 over 3 factorial. X to the 4 over 4 factorial. Do one more for effect. X to the 5 over 5 factorial. And you keep going. Find these derivatives term by term. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 factorial is 2x over 2 factorial. The derivative of this next term is 3x squared over 3 factorial. 4x to the third over 4 factorial. 5x to the fourth over 5 factorial, and so on. Well, we can simplify this. 0 plus anything we don't really need. 1. 2x over 2 factorial. Let's see, the 2 factorial is 2 times 1, so the 2 on top and the leading 2 will cancel, and you're left with, well, 1 on bottom, or just x over 1, or x. Same reasoning. 3 factorial is 3 times 2 times 1. So the 3 on top will cancel with the leading 3 on bottom, and you're left with 2 times 1, which is 2 factorial, and x squared on top. 4 factorial is 4 times 3 times 2 times 1. The leading 4s will cancel, and you're left with 3 times 2 times 1 on the bottom, which is better known as 3 factorial, and x cubed on top. Same game. 5 divided by 5 factorial. The 5 will cancel the leading 5, and you're left with 4 times 3 times 2 times 1 on the bottom, and x to the fourth. But note, this is just the original series we started with. The original series is in fact just this derivative. So the derivative is equal to the original series, which is just the original function. Put that together to answer part B. What is a common name for this? What is a common name for a function who's equal to its derivative? And this is exactly the property that this function has the same property and therefore is the same as e to the x. What this tells us is that this function, that this series, is in fact a way to represent, the function e to the x, which means this series is not just close to e to the x, this is exactly the same as e to the x. So if you want to to calculate values of e to the x, we don't need to know we don't need to know the infinite decimal expansion of e and start multiplying that by itself. Instead, what we can do is just take this polynomial representation of it and just substitute in whatever exponent we want for e in for x, and tell our calculator or our computer to hit enter. Polynomials are way easier to find expression exact values of than these bases that are irrational. So since we have this expansion, we can use this expansion to find powers of e, and this is exactly what your calculator is doing in the background. If you ever when you're calculating values of e, your calculator doesn't have e to a bunch of decimals saved in it. What it does have, in fact, is this series up to in enough terms in this series so that the error in the term is smaller than the number of display digits in your calculator. And when you type in an exponent, it goes through and fills in each of these x's with that exponent in multiplies and sums. On the homework set that goes along with this, the first question is a question very similar to this, where there's a power series, and you're going to explore some properties of this power series, and then use that to determine some common names for those functions, similar to what we did here.